we have a curve defined by the vector function r of t, and we ask what's the distance between 2 points along the curve as measured by a particle traveling along the curve. We know that r prime of t is the limit as delta t approaches 0 of r of t plus delta t minus r of t divided by delta t, which is the limit as delta t goes to 0 of delta r over delta t, where delta r is the vector from the r of t point to the r of t plus delta t point. So we could say that our delta r is here. Now, what do we mean by delta s? We mean distance. It should be clear that if this is a fairly short segment of the curve, delta r comes very close to coinciding with the curve over this interval. So that in this case, delta s would just be the magnitude of delta r. Now, the magnitude of delta r, if we consider this definition, is approximately equal to r prime times delta t. And the parentheses make that look like r prime is a function of delta t. R prime is a function of t. I'm not explicitly writing the t dependence here. So delta s is just how far it is from here to here. That's the magnitude of the delta r vector. The delta r vector is the product of our r prime vector and delta t. Rather, is approximately equal to the product. And if delta t is close to 0, then this approximation is very close to being exact. If we want to find the distance between two more separated points of a curve, where the curve might change direction drastically in between, so that the distance from here to here along the curve is significantly greater than the distance from here to here along a straight line, then we consider the following. We partition the interval between A and B, and let's write out that partition. Okay, we partition the interval between A and B so that A is less than or equal to T1 is less than or equal to, and let's, what I really want to write here is we want to partition the interval A less than or equal to T less than or equal to B. And that partition will consist of a set of T values that run from A to B by what we were going to consider small increments. So the partition itself can be written like this: A equals T sub 0, which is less than T sub 1, less than T sub 2, and so forth. Somewhere in the middle we'll have a typical interval that runs from Ti to Ti plus 1. And finally, we end up with T sub n, which equals B. So now we've got a partition of our time interval from A to B. The corresponding R vectors will then have terminal points that run from R of A, which corresponds now to our T naught point, to r of b, which is our t sub n point, and we'll have a number of points in between. We consider this to be a large number. And let's just take a interval here, an interval, and let these 2 points here indicate the positions which correspond to the points r of t sub I and r of t sub I plus 1. So these 2 positions will correspond to the vectors r of t sub I and r of t I sub 1, t sub I plus 1. We'll have a number of such intervals, and that number of intervals is going to increase. The widths of the intervals is going to decrease, and in the limit we're going to sum up all the distances over all these intervals to get the total distance from r of a to r of b, and that limit is going to approach an integral, and we'll see what that integral is. So we partition our interval from a to b. We take a typical partition, a typical interval in the partition, from t sub I to t sub I plus 1. We indicate these positions, label them r of t sub I, r of t I sub 1, and think about how far the object is going to move over this particular interval. Since I is arbitrary, it could be any of these intervals, so we're going to have a general expression for how far the particle would move on a typical interval. We'll analyze that in a minute.